our chosen alternative for the existing intersection is a roundabout design. That means for my personal goals, I had to increase the user safety at the intersection, as well as improve the level of service to B or higher. Some of the general considerations for my particular design were the horizontal and vertical alignment geometries, as well as the pavement design. So one of the things that really drew us to a roundabout over the other alternatives was the fact that it had some unique safety features. So if we look here at figure 1, this is a typical four-legged intersection. And at this intersection, you're typically going to have about 35 potential conflict points. And most of those are either head-on collisions or right-angle collisions, which are generally more dangerous accidents. If we add in our fifth leg, which we have at our existing site, that raises the potential to over 75 conflicts, which is why we see so many conflicts at our existing site on our accident report. In comparison, a roundabout limits those collisions to only 2 per entry. So we have 5 legs at a proposed site, which means we have a potential of 10 conflicts in total. And that's an 86% reduction from the existing site. Not only that, but these accidents are limited to side swipes and rear end collisions, which are generally more safe in terms of accidents. So Sean briefly touched on the level of service of an intersection. Again, this was in one of my goals for the project. And because a roundabout is neither signalized nor stop controlled, the majority level of service comes from the geometry of the roundabout. So shown here in figure 3, this is our proposed geometry for the existing site. As you can see, it has 2 lanes through the roundabout, and it has a 15-mile-an-hour posted design or recommended entry speed. Now this differs a little bit from our design speed that we designed it for, just to give the users a little extra factor of safety if they want to move through the roundabout more quickly. There's several things that go into the actual geometries of a roundabout. I'm going to talk about the design vehicle and the deflections. So the design vehicle more or less is just the largest vehicle you can expect to move through a roundabout or roadway on a given day. And because of the roadway class of our existing intersection, we went ahead and chose the WB50 design vehicle, which is just your standard 55-foot trailer or semi-truck that you see pretty much every day. So our biggest concern with this design vehicle was the small angle of the existing site between Roosevelt Road and Calumet Avenue. And we were just wondering, can our design vehicle make this maneuver if it's necessary? So to accommodate that in our design, we first flared Roosevelt Road farther east into the existing parking lot site. And then we also added an additional truck apron between Calumet Avenue and Roosevelt Road. Again, this just gave the design vehicle a little more room to make that maneuver if it was needed, and to give the passenger cars the appropriate amount of deflection as they also made that movement. So Sean's going to open up. I have a quick animation. If you're not sure quite how a truck apron works, I have just a brief animation here. So this is our truck apron that we installed between Calumet Avenue and Roosevelt Road. And as you can see, the cab of the design vehicle actually remains in the roadway at all times, while the trailer will actually mount the truck apron. It didn't work real well. Okay. Back in there. Okay, as I stated earlier, another one of the things that's important to the geometry of a roundabout is the deflection through the roundabout. Some of the things you have to consider is if you make the center island too big, more than likely the design vehicle is not going to be able to maneuver through the roundabout effectively. However, if you make this center island much smaller, or you don't install a truck apron around the center island, then your passenger cars are more tempted to take a shorter path, as shown here in figure 9. Again, this just facilitates higher rates of speed, which makes it much more dangerous for the users. So it's important to find the appropriate balance in the design when you're designing for deflection. All that said, once we kind of had our geometries laid out for the roundabout, we were able to feed that into a traffic modeling software, which allowed us to estimate the level of service of our intersection. And as I stated earlier, we wanted this to be a level of service B or higher. And from that software, we were able to confirm that we did achieve that at a level of service B. So in conclusion, my total project or construction cost for the transportation part of this project was roughly $1.1 million. And this included things such as pavement removal, pavement installation, signage and striping, all that jazz. So now I'll go and pass off to Kyle, and he'll talk about the water resources.
Thank you, Derek. My name is Kyle Campbell. I'm the head water resource engineer for Negotium Engineering. And for my portion of the project, I had two main goals, and that was to achieve a sufficient amount of stormwater storage on site, have that water soak into the ground instead of just passing it on to the storm sewer. And also that any water that does leave our site, it's clean. It's removed of any pollutants that it may have gathered in its journey to the site. Also, I designed the storm sewer that takes the water from the roadway to the the stormwater control measures listed here, and also any site grading that needed to be accomplished. Here's just a quick overview of the stormwater control measures that I have designed for. I've strategically placed them around the whole entire intersection so that treatment and storage can take place throughout the whole intersection. Here we could see the permeable pavements on the west side of Calumet Avenue and the west side of Roosevelt Road. The shaded gray areas are the rain gardens, and we'll talk a little bit about them in a little bit. And also, we'll be using hydrodynamic separators in series with the rain gardens to get that pollution removal. And why we're using rain gardens? Well, rain gardens, they reduce the amount of runoff that you get on site. Also, they increase the aesthetics of the intersection. The flowers and shrubs that you place in them are very pleasing to look at. Also, they recharge the groundwater. They're able to store that water and then soak it in after a period of time and replenish the groundwater. And then you can see the shrubberies and flowers. It looks nice. Also, we're using a permeable pavement for some of the same reasons. We get that storage and that water quality benefit. And not only that, but they're better than normal concrete sidewalks because of the less salt application in the winter. Instead of with normal sidewalks, water sits on top and freezes, whereas with these, water is able to infiltrate into the cracks rather quickly, so it doesn't have a chance to freeze. And the hydrodynamic separators we'll be using, I'll just quickly explain how these work. Water enters in the inlet, and it swirls around. The sediment drops out, and then the clean water flows out. It's kind of like a swimming pool. You make a whirlpool, and all the dirt goes to the middle. Same sort of aspect. So water will be collected off the road, flow through the storm sewer pipes that I've designed, and be treated. And then further flow into the rain gardens to get further treatment. We want to make sure we get that clean water, because that's what our client has wished we achieve. Total amount of money I have projected that it will cost to construct is just around $315,000. And now I'll hand it off to Eric, who's going to show you some pretty cool bridge renderings.
Thanks, Kyle. So as lead structural engineer, I was tasked with creating two bridges to cross the 8 lanes of traffic that are over Calumet Avenue and Roosevelt Road. And also we wanted to unify the businesses to the north and south of the intersection. So the most cost-effective alternative chosen was a steel bridge with timber decking. And we wanted to use anti-corrosive steel as well as hardwood decking just because of the harsh conditions that Indiana suffers just like within a week sometimes. And then we also wanted to use steel rope, metal grading stairs, and then for ADA standards we wanted to use exterior elevators. Here's just a quick overview of the bridges. We have bridge AED and then bridge CD. At each location we have stairs as well as an elevator. And this is what you don't want to happen at your bridge. You don't want a wobbly bridge. You just want to account for the frequencies within the bridge, make sure you're designing everything right, make sure all the supports are well supported, and you get a bridge like this. So we have our steel grading stairs, our elevators, our beautiful arc members, lovely shade of green. Here's just another rendering of the bridge. We have, you can see the beautiful red decking, elevator pad again. Just another view. And then we have the overall span of AED, as well as what it would look like if you were actually on the bridge. And then over here we have some shrubbery that you could be able to hang on to the bridge itself. In the summer months, we would have flower pots. Winter months, we could even have Christmas trees. And then we could even have signage to indicate what events are happening around in Valparaiso. So here's just some logistics. We wanted to ensure that vehicle clearance of 15 feet. And then here are some of the actual sections I used, which you can go ahead and purchase and build your own bridge if you want. So the overall cost was just shy of $400,000. This included timber decking, the heavy crane equipment to actually place the bridge onto the site, concrete, and elevators. With that, I'll pass it on to Sean.
All right, thank you, Eric. And so as previously mentioned, there's a few contaminants on site, mainly fuel contaminants. And so what we need to do is we need to treat the soil and also the groundwater and any vapors that may raise through the soil. And here's just some resources I utilize just to make sure that we're meeting federal standards. And then this is a table just to show different technologies you can use to remediate different kinds of contaminants that you may have. So to start with the groundwater portion, here's just a schematic of the 3 units we use. These are granulated activated carbon units. And essentially these are full of activated charcoal. And once we pump the water out of a well that we are going to install, it runs through each of these units and removes all the VOCs and the fuel contaminants of the water. And then we can discharge that into the sanitary sewers. And for the soil we just decide to dispose of any contaminated soil. So if we excavate lower than 4 feet, we just assume that's contaminated and we have that disposed of off-site. And so for the contamination plume, this was given to us per a soil contamination report. It's located on the northwest portion of the site, and this little pink dot here and there is the location of the well that we want to install, and the red line here shows the effectiveness of the well. So once we turn on the pump, this is the area in which the water will be sucked to the well, just to make sure that we can treat the entire plume and prevent any vapors from rising up from the contaminants as well. And so here's a schematic of the well that we want to install. The red line here is just the drawdown effect of the pump when you turn it on, so the water level will be sucked down slightly. And also around the well, we have gravel packing, and this is just to help increase the flow of water to the well. And also in conjunction with Kyle, our water resource engineer, we created a storm water pollution prevention plan. And so this is just to make sure that we're not allowing sediment to go into the inlets and further pollute the water. And so to wrap up the environmental portion, the groundwater is expected to be about $235,000, and the disposal of the contaminated soil is about $120,000, which totals to approximately $355,000. And with that, I'd like to pass it off to Yosef, who will talk to you guys about the geotechnical side.
Thank you, Sean. So as Sean said, I'm the geotechnical engineer for this project, and my goal for this project is to design a foundation for the pedestrian bridge. So Eric, our structural engineer, called me up one day and said, I need a foundation for my bridge. So after I discussed my payment of of my design, I started my design. So let's start. Okay, as we can see, if I wasn't in this project team, this is what it would happen. This is the famous Tower of Pisa, and as you can see, it's not quite straight. I don't know if you noticed, but and as you can see, Professor Polito is not too happy about that. That's his sad face, by the way. Okay. All right, let's get serious now. Okay, so the first part of my design is the bridge. So for the bridge, I have driven piles and pile caps. So what piles are used for are cylindrical concrete tubes, which go into the ground, as you can see here in this picture, and they can hold the load from the bridge. And the pile caps are put on top of the piles to transfer the load from the bridge to the pile caps. And next is the stairs. So the stairs, for the foundation of the stairs, it's quite simple. We just had to put a piece of slab under it with some reinforcement, as you can see. And we call that slab a mat foundation. And I chose a 15 by 15 foot mat foundation. And next is the elevators. So the elevators have different components. We have retaining wall, pile cap, and piles. As I mentioned before, the piles and pile caps are there to hold the load of the elevators. But for the retaining walls, a retaining wall, so let me just explain, is a wall that that handles the pressure from the soil, so it doesn't crack into the hole. And we have four retaining walls to create a box-like structure. And inside this hole, we will put the shaft and the components of the elevator inside there. As you can see, this is a retaining wall. They're just putting in the reinforcements for that, and I think they're about to put the concrete in. So these are some of the design criteria and assumptions I used. And my total cost for this project is $198,000. That includes piles, pile caps, retaining wall, excavation, and mat foundations. And now I'll pass it on to Sean to talk about the total cost.
Thank you, Yosef. So now just to wrap up our presentation, we want to provide you guys with the overall cost of this project. As you can see in this table, we have each of the disciplines and then their costs, which the construction cost totaled to approximately $2.3 million. And then we also have our design costs just for the hourly fees that we charge for designing this. And adding those together and adding a 10% factor just to account for any variations in what construction companies would expect to bid this project for brings us to a total of $2.7 million. And with that, we'd like to thank you guys for coming out and supporting us and invite my group back up and open the floor for questions.
Well, we just figured ramps would pick up a bigger footprint than elevators. Or he asked why we used elevators at each locations or entrance locations, and for that, or my answer would be that ADA standards require a 2% slope, and that would require like 300 feet just to achieve that 15-foot height of the bridge, and I just wanted to use elevators to facilitate, or to just decrease the footprint of the overall bridge. Michelle? Too long.